All right, you guys know I like Mathematica, right? Is that impression?
Not yet.
I like it more and more every day. I do want to encourage you that it is worthwhile to learn. Not only for this class, but also for other math, physics classes, chemistry classes even, maybe even biology classes. And it can help you in the job market, even if you don't decide to go to grad school. If you go into the job market, it can help you in the job market. For example, there's data-based things. That thing in the documentation center says engineering data and computation. Financial stuff is in Mathematica, financial data and computation. These are all documentations of things that you can look up to help use Mathematica for lots of different things. Social, cultural, linguistic data. Okay, it is quite diverse in what it can do. Graphics and networks, visualization, it can do image processing and that kind of thing. It is a lot, okay? People think I'm an expert in Mathematica. No, I'm not really. Maybe compared to your average person, of course, but I probably only know about 1 or 2% of all that Mathematica can do, okay? And that, relatively speaking, I guess, makes me an expert. I guess this image is probably, that section probably has some image processing stuff in it. It's got tutorials, it's got probably some videos on the Wolfram site. I know there are some that you can use to look up some of those things. You can even use Mathematica for Valentine's Day. Long about 6 years ago, I think, 2009 or so, I decided to make my wife a Mathematica Valentine. And here's the code I came up with. And what does this code do? My wife's name is Lynette, and here is what it produced. Isn't that great? So that for that year, 2009, that was my Valentine for my wife. I showed it to her, and she's like, "Oh, that's my Valentine?" And I'm like, "Yeah, aren't you impressed?" And well, I think she thought I perhaps put it together in like 5 or 10 minutes. But no, it actually took me a couple hours to put this together because I had to experiment with it to get it to look right, okay? So I spent a couple hours on it, and once she heard I spent a couple hours on it, then she was glad that I did. So you can use Mathematica for lots of different things. All right, and differential equations, of course. What are we going to do today? Well, first I want to talk about slope fields a little bit more and say that you should be able to relatively quickly sketch slope fields without technology, without Mathematica, for relatively simple examples. Whether those examples are pure antiderivative problems, where the right-hand side is f of t, autonomous problems, where the right-hand side is f of y, or what's harder typically is the mixed problems. Pure antiderivatives, the slope field is constant along vertical lines. Autonomous, the slope field is constant along horizontal lines. Mixed, it's not necessarily constant along horizontal or vertical lines. Okay, but for simple examples, we should still be able to do that. So that's one thing we'll do here at the start. We'll talk more about existence and uniqueness and that thing that's the supplementary reading assignment. Part 1, there's going to be a part 2, and maybe even a part 3 eventually. Part 1 is probably the easiest one, so we're going to warm up toward harder stuff there. I'm going to talk about that some in class today. And then we're going to get on to section 1.6, which is about phase lines, sink sources, and nodes for autonomous differential equations. So what do I mean by you should be able to sketch stuff by hand, slope fields by hand, for simple examples? Well, before I do an example, here's an example of something I didn't know about Mathematica until a day or two ago. There's a professor named David Arnold at the College of the Redwoods in California who happened upon my videos, and he has gotten into using Mathematica, and he's found plenty of things in Mathematica that I didn't know about even. I just never tried it. And this SetOptions thing allows you to set your vector scale, your vector points, lack of a frame, axes label ahead of time whenever you want to use vector plot. So if you have this stuff, you can enter it, and then you don't even have to add it inside your vector plot, and it will automatically be there. Like we'll see the t and y axes labeled italics and large without actually having it inside the vector plot here. So that's pretty nice. You also can highlight this cell if you want within this notebook and go to cell and cell properties and initialization cell. Click on that and it will be called what's called an initialization cell, which means whenever you open this notebook, you don't even have to enter this. You just go down here, enter this, and Mathematica will come up with a message, do you want to run all initialization cells? And if you click yes, this cell will automatically get entered, and you never even have to hit enter on it, as long as you do that from that point on. Okay, you can use it whenever you want. So anyway, coming back to this example, this is an example where you should be able to relatively quickly sketch the slope field. It's a pure antiderivative problem. dy dt equals t cubed minus 4t. How could you sketch the slope field relatively quickly? Rough sketch. Well, you could first of all factor this to figure out where it's 0. Does this differential equation have any equilibrium solutions? No, it doesn't. Okay, it's tricky. Doing this makes you think it does, but remember that only happens when the right-hand side is just dependent on y, when it's an autonomous equation. This is dependent on t, the independent variable, not autonomous. Autonomous kind of means independent of t in the context of differential equations. That side depends on t, it's not autonomous. And so the places where this is 0, at t equals 0, t equals 2, and t equals -2, do not correspond to equilibrium solutions. They correspond to locations, vertical lines where your solutions have a horizontal tangent. Local max, local min, or perhaps just an inflection point. Usually a local max or a local min. If I make the slope field, if I try to sketch the slope field quickly by hand, I'd want to mark -2, 0, and 2 as being vertical lines where the slope marks are horizontal. Put little horizontal line segments along those vertical lines. And again, that doesn't mean that you've got horizontal solutions, constant functions that are solutions. That doesn't happen here. That's just where the tangent line is horizontal. This right-hand side function here, you could graph it, but if you do, you're not graphing a solution. You're graphing it to see where it's positive and negative to help you decide where your slope mark should have positive and negative slopes. It's a cubic, positive coefficient. Its graph is going to look about like this. It's going to be positive when t is greater than 2. So you're going to get positive slope marks. Slope marks having positive slope when t is bigger than 2. They are going to get larger and larger in slope as t continues to the right of 2. Negative outputs for this function when t is between 0 and 2. So in the slope field between 0 and 2, you've got negative slopes. Be careful here. Let's see. Yeah. And the negative slopes are going to be most negative. Actually, not exactly halfway between 0 and 2, but somewhat close to halfway. It's probably okay if you draw it about like this. Positive slopes between -2 and 0 because this function has positive outputs there. I I'm drawing it to look like the slope is maximized halfway between -2 and 0. That's not true again, because for cubics, this maximum is not halfway between the 0 and -2, even though I kind of draw it that way. We won't worry about that. And then negative slopes in the slope field when t is less than -2, because the outputs of this function are negative when t is less than -2. Okay, solutions follow the slope field. So to draw an arbitrary one, it'll look about like this. Oops, did I make a mistake? I must have made a mistake. Yes, I made a mistake with my slopes over here, sorry. Something about like this. And actually, by symmetry, this, I didn't draw it perfectly, but this would be an even function with the solution. That is a solution right there, approximately. Here's its formula, just it's a pure antiderivative problem, just integrate the f of t. Your integration constant would be a plus c, and that does happen to equal the initial value, y0. Here I'm plotting the plot with initial value 0. I could also put this inside of manipulate and let y0 be the animation parameter to see the graph get shifted up and down. I'm not bothering to do that for sake of time. I could have done it ahead of time. Maybe before I put it on Moodle, I'll go ahead and do that to allow y0 to change. And that's going to be vertical translations will be solutions. Because the slope field is constant along vertical lines. So along any vertical line, your slope of a solution is constant. You translate the graph up and down, you get another solution. Okay, this is like a calculus 1 type of differential equation, these pure antiderivative problems. What about an autonomous example? Maybe we should do the exact same function, except think of it as a function of y instead of t. Although if I do, I'm not sure how nice the solution function is going to be. It's not going to equal this thing here. Delete it for the moment. And then go ahead and enter this function of y. Let's go ahead and see what d-solve value produces, if it's possible. Theoretically, it's possible, I think. Although as a practical matter, I'm not sure how nice the answer is going to look. Probably will not look so nice. Oops, that d-solve. I want d-solve value. Giving you some warning about inverse functions. That's not as bad looking as I was expecting. Excuse me. Did I do it? F of y is that? Is that really right? It doesn't. It seems kind of crazy to me that it would be so simple, and I'll get the AT. Well, let's just see if we put it in the slope field. I'm feeling like this can't be right, but let's see what happens anyway. Here, this is an f of y. Let's do it by hand first. So f of y in this case is y times y minus 2 times y plus 2. Same graph as over here, except you change the labeling of the axes. Change that to a y and this to an f of y. You draw the same picture though otherwise. You will have equilibrium solutions in this case at -2, 0, and +2. The slope field is constant along horizontal lines for autonomous equations. And along those 3 horizontal lines, the slope marks are going to have 0 slope. I'm drawing a bunch of dashed lines here, but you may as well just draw the equilibrium solutions. I'm having trouble drawing that perfectly. like that. Again, in this case, when y is bigger than 2, slope marks have positive slopes. So when we're above the horizontal line at y equals 2, we've got positive slope marks. That gets steeper and steeper as y gets higher and higher, leading to solutions that look like that. When you've got y between 0 and 2, you've got slope marks with negative slope, leading to solutions that look like this, and that are horizontal translations of each other. Y is between negative 2 and 0. You've got positive outputs over there, leading to slope marks with positive slopes, leading to solutions that look like this, and are horizontal translations of each other. Finally, when y is less than negative 2, the outputs of f of y are negative, leading to slope marks with negative slope, leading to solutions that look about like this. Yeah, something must be wrong here, I think. It just seems too simple. And is that slope field even right? Is that right? Maybe. I think D solve value is not working here, unless I'm doing does it look like I'm plugging in wrong? It looks okay to me. In that initial condition, I plugged in y0 equals 1. It's not even going through the right point there. Though it does look like a solution. So it seems to be giving me some sort of solution. I'm just not exactly sure what. I'll try to fix it if I can, if it's possible, before I put it on Moodle. And we'll see next Monday whether or not I was able to fix it. I'll talk about it in class too. Let's move on though. What about a mixed one? I'm not going to bother with the Mathematica. Let's just consider a simple mixed one by hand. Probably does need to be fairly simple to be able to fairly quickly, roughly sketch it. For example, 2t minus y. Fairly simple. There are going to be no equilibrium solutions, but you can find fairly quickly a curve. In this case, it's going to be a line along which tangent lines are horizontal. 2t minus y equals 0 if and only if y equals 2t. So along a line through the origin with a slope of 2, the output of the right-hand side function is 0, meaning the slope marks in the slope field are horizontal. These are not slope marks here. The slope marks along that line are going to be horizontal. (2t minus y is greater than 0 if and only if y is less than 2t. Does that make sense? Y is smaller than 2t. Solve that inequality for y. I switch the direction. So when you're below that line, you're going to have positive slope marks. Slope marks that are positive in slope. And probably constant, it looks like along these slanted lines of slope too. It looks like to me. Probably something like that. And then when y is bigger than 2t, when you're above that line, 2t minus y is going to be negative and they'll have negative slopes. Looks like. So, I'm feeling a little uncertain about things. I hope I did this okay. I think I'm thinking about it correctly. I think that Mathematica thing, where the formula came out so funny, is kind of throwing me for a loop. But I think this is okay. And now I'm not so sure. I don't know. I think you're going to get solutions that look like this. Maybe we should check that. Positives? Oh, okay. I'm full of mistakes today, it seems. Okay, yeah. Negative slopes over there. It felt funny that it would be that way. So something more like this is what your solutions are going to look like. Okay, as a rough approximation. Okay, let's get on to the theoretical stuff about existence and uniqueness as the next subject here. Related to that extra reading to do. And it's actually going to be important for us to get to that final subject for today, the phase lines. So here's the theorem I showed you at the end of class on Wednesday. So you don't have to write this down, but I would perhaps recommend writing it down after class, maybe looking at the video and writing it down, or downloading the notebook and writing it down, just to think about it as you write it down, and do think about it, don't just transcribe it without thinking. Theorems are statements of important mathematical facts, and they always have hypotheses. Now in mathematics, hypothesis really means something different than in science. In science, a hypothesis is essentially a tentative theory about something. You have an idea about the way the world works, and then you got to test your hypothesis, and maybe it eventually becomes a theory, which is very broad. Theorems are different, and hypotheses are different in that than in science. A hypothesis of a theorem is a statement you assume is true in order to prove the theorem. We're going to assume that f is continuous. And to keep it simple, we'll say for all real values of t. That's the thing we are assuming in this statement is true. And then the part that comes after that, the then, which includes in this case 4 parts, you want to prove that those things follow from the initial hypothesis. Sometimes a hypothesis is called a premise. In this case, the conclusions are, first of all, the solution for any initial value problem like this exists for all t. Secondly, if you got a solution and you add a constant to it, you get another function that's also a solution. Vertical translations of solutions are still solutions. Third, if you've got 2 solutions, then this equation relates them for some constant, meaning 2 solutions, 2 distinct solutions are vertical translations of each other. And finally, the solution does not only exist, it is unique. I actually talk about this when I teach Calculus 2. I think a few of you might have had that from me. Remember what's the essential reason why all this is true? We'll focus on A and D especially.
Constant. For like intervals, I guess you could say. Because if it wasn't constant, you wouldn't be able to add something. There'll be like parallel solutions in a sense.
Yeah, I mean, I think you're talking about the fact that vertical translations of solutions are still solutions. So that's getting to the slope field idea. I want to focus more on A and D, that solutions exist and they're unique. I did talk about this in Calculus 2. It's related to a very fundamental fact in calculus. I use the word fundamental on purpose. Fundamental Theorem of Calculus could be thought of as an existence and uniqueness theorem. Oftentimes people write the Fundamental Theorem of Calculus as its equation in a couple different forms. It's a theorem, it's got hypotheses. Essentially, it's good enough for us to assume the function you integrate is continuous, just like I'm assuming here. The form most people think of is that if you want to integrate a function little f that's continuous over this interval from a to b, and you can find an antiderivative, capital F, that you can calculate that integral by doing that difference. Okay, I'm not writing this as a theorem, I'm just not writing out the hypotheses. I'm just verbally saying that little f is continuous. If you can find an antiderivative, capital F, meaning the derivative of capital F is always equal to little f over this entire interval, then you can evaluate this definite integral by doing that. That's the form you're most used to. Antiderivatives can help you evaluate integrals. But there's another form of the fundamental theorem of calculus that in a way is a bit more general, that says not only do antiderivatives help you evaluate integrals, integrals can be used to define antiderivatives. If you differentiate an integral where the upper limit of the definite integral is a variable, t, differentiate this thing which it's a function of t. I'm using a tau there, sometimes called the dummy variable. Tau is the Greek version of t, to emphasize that that's not the variable for this function, that's the variable. I'm using the integral, defined in terms of limits of Riemann sums, to create a function of t, and I claim if I differentiate this function with respect to t, what do I get? It's pretty simple. I get little f of t, yeah. In other words, this expression, as a well-defined function of t, is an antiderivative of the integrand, little f. We have created, mathematically speaking, an antiderivative. In other words, we have solved, we have found one solution of this differential equation. That function right there. For any a, if I assume little f of t is continuous for all t, I can pick any a I want. That's an a, not a 9. And that's the solution. And moreover, since if you integrate from a to a, you get 0, it solves that initial value problem. That y of a equals 0. So what I'm saying is, it's the fundamental theorem of calculus that guarantees the existence part of that in the case where it's a pure antiderivative problem like this. The fundamental theorem of calculus is the existence theorem for the pure antiderivative problems. Uniqueness, the part D follows actually from part C. Parts B and C follow from the fact that, well, the derivative of a constant is 0. And the fact that if you differentiate a sum, it's the sum of the derivatives. That derivative is 0. Goes away. Part C actually follows from something sometimes called the constant function theorem. The fact that if a derivative of a function is always 0, the function must be constant. Okay? The proofs are in the extra reading assignment. So you should make sure you spend the time to do that. But that's all I wanted to highlight about this right at the moment, is that it's the fundamental theorem of calculus that guarantees this. We're doing it in time. Let me do a simple example to illustrate this in kind of a strange way. Let's say we have a relatively simple piecewise defined function for little f. let's say this is little f of t. And I'd like to create an antiderivative of this without sort of realizing what the antiderivative, sort of guessing what the antiderivative would be ahead of time. I'd like to think about the signed area interpretation of the definite integral to help me create an antiderivative of this function, a solution of that differential equation. Again, by thinking about integration in terms of signed area. And you've got two cases essentially. One case is when t is between 0 and 1 because that's one piece of the piecewise linear function. And the other case is when t is between 1 and 3 because that's the other piece. If t is between 0 and 1, what's the value of the integral? It's the area of this triangle. 1/2 base times height. One half base, the base is t. What's the height? What's the height of this triangle in terms of t? F of t, which is, because of that line of slope 2 through the origin, it's simple, 2t, yeah. The 2's cancel, leaving you with t squared, which, yeah, the derivative of t squared is 2t. What about if t is between 1 and 3? It's the area of that triangle plus that rectangle. The area of this triangle right here is 1/2 base times height. Doesn't depend on t. 1/2 times 1 times 2. 1. The area of this rectangle is base times height. The base is t minus 1. The height is 2. Base times height, t minus 1 times 2. If t is between 1 and 2, or 1 and 3. Which simplifies to 2t minus 2 plus 1 minus 1. This again simplified to t squared. Yeah, the derivative of 2t minus 1 is 2. These two pieces, the t squared and the 2t minus 1, do come together in a continuous way at t equals 1. If you graphed capital F of t versus time, you get t squared right there, and you get 2t minus 1 starting right there, and its value at t equals 1 is 1. You get a straight line after that point. This is not a parabola overall. It's only this piece that's a parabola. This piece is straight. That's the solution, for t positive at least, of this differential equation that goes to the origin, this initial value problem, for this function right here. So the reason I did this again was that I'm emphasizing that integrals can also be thought of as defining antiderivatives. They can be used to calculate antiderivatives, or you can calculate the antiderivative in some other way. Excuse me, they can be used to calculate integrals when you can calculate the antiderivative in some other way. They can be used to define antiderivatives also. There's a fairly simple case. The example I showed you on Wednesday is a less simple case. When little f of t is sine of t squared, indefinite integral of this involves this FresnelS function, which you've never heard of before, but it does exist, and essentially the integral defines it when you think of the integral as a definite integral. FresnelS does happen to go through the origin. You can approximate its values by doing numerical integration, probably Simpson's rule for sine of t squared. Make sure you spend time thinking about that. That's worth doing. As an example, if I think of it in terms of numerical integration, I can do n integrate sine of t squared. I'll go ahead and enter this. T goes from 0 to 1. I should get a good approximation to this FresnelS function that involves the square root of pi over 2 in front and the square root of 2 over pi inside when t is 1. The graph down that I'm about to show you at t equals 1 should have a value close to 0.31. Right, there's t equals 1. There's the output. That should be close to 0.31. That's 1. That's a half. Close to 0.31 right there. Okay. What about existence and uniqueness for autonomous equations? There's a way you could state the theorem in sort of the simplest case for autonomous. I'm assuming little f of y now is continuous and has a continuous derivative for all values of y. Okay? Again, I could assume it's not for all values of y, but for all values of y in some interval if I wanted to. But just to keep it simple, for all real values of y. By the way, when this function is not only differentiable, but also the derivative is continuous, we say f is continuously differentiable. That is an official term in math, and it's mentioned in your book. Derivatives actually don't have to be continuous. There's some pretty strange examples out there where the derivative exists everywhere, but it's not continuous everywhere. At a time, maybe one day I'll show you. I can probably show you a quick example of such a function. Anyway, under those conditions, the solution of any initial value problem exists and is unique. Actually, you can get away with just assuming f is continuous to get existence, but then you don't get uniqueness, actually, and the book addresses that in the reading with an example. It exists as unique, at least over some possibly very small interval. And oftentimes what happens to make your interval kind of small is your solution ends up going to infinity pretty quickly. There was an example in the book like that. Or it goes to having like a tangent line that's vertical. Okay, I think there was an example in the book like that as well. Moreover, part B, and we already knew this, horizontal translations for autonomous equations, horizontal translations of solutions are still solutions. If you subtract any h to translate the graph to the right of h is positive and to the left of h is negative, you still get a solution. The initial value problem, though, changes. Y of h equals y0 would be the new initial value problem for that. I guess I'm assuming, I didn't state this perfectly. I should have stated that phi of t actually solves dy t equals f of y, comma, y of 0 equals y0. I should have said that before I put this back on Moodle and make that change. Okay, so this is sort of stating stuff you already knew. And essentially, existence just gives us comfort. It knows that, it helps us know that we're not doing our work in vain, even when you can't find a formula for a solution. Uniqueness ends up being more important for us in terms of practical application. Saying distinct solution curves can't touch each other. Okay? And once again, I'll emphasize this is not about nothing. It is important. There are some equations that are just too complicated to find a formula for. So you'd want to know the solutions exist before you try to approximate them with Euler's method, for example. For example, I'm sure I could come up with an autonomous example that's complicated enough that I'm going to bet there's no closed form solution for it. Perhaps if I did this, sine of y of t, let me me square it for good measure. Square it on the right like that. That's autonomous because when you write it by hand, the right-hand side would be sine of y squared. I'm going to go ahead and take the risk that this doesn't have a simple form for the solution. I could be wrong. Well, I'm sure if it exists, it's not simple. It's not an elementary function. Maybe somebody's given a name for the solution. Let's see. It's working really hard. Thinking, thinking, thinking. We'll let it think, okay? We'll see if it comes up with anything or if it gives up. What we're going to do for the last bit of time here today is start you thinking about these phase lines. And that's mostly what your completion assignment is about for next Monday. Tell me when it's got an answer or has given up. Let me know about that, okay? Phase lines. Phase lines are always made for autonomous equations. Not pure antiderivatives and not mixed. It's got to be an autonomous equation. And by the way, the autonomous equations ultimately are the main kinds of examples we do consider. Sometimes some simple non-autonomous equations, but mostly in this class we consider autonomous equations. So it's an autonomous equation. What a phase line does, in a nutshell, is it takes the slope field and the solutions in the slope field and kind of compresses them to just being on the y-axis and focuses on where the equilibrium solutions are and where the other solutions are increasing and decreasing. For example, well, we can do the same example that we did earlier today. This one, which could have been written as a y cubed minus 4y instead. Here is the slope field, partially erased. How do we compress the information in the slope field onto the y-axis? What we do is we create dots along the y-axis at the same values as the equilibrium solutions. And then we don't call them equilibrium solutions anymore, we call them equilibrium points. Make dots here, here, and here. I'm drawing it on top of the slope field. You'll see usually in the book they don't bother drawing the slope field even, or else they draw the slope field and they put the phase line right next to it. Either way is okay, although it's going to be usually quicker to just draw the line and label these points. What about for the non-equilibrium solutions? How do you compress the information that's in the slope field along to the y-axis? It depends on whether the solutions are increasing or decreasing. And for autonomous equations like that, it will be one or the other in between the equilibrium points. Up here, when y is higher than 2, the solutions are increasing, so draw a vertical arrow along the y-axis, the phase line, to indicate that solutions are increasing. Between y equals 0 and y equals 2, solutions are decreasing, so draw a vertical arrow going downward. That one's going upward, this one's going downward. I think I forgot to say upward. Vertical arrow going upward when y is greater than 2, downward when y is between 0 and 2 because solutions are decreasing.
Yeah, it is.
Oh, it stopped, huh? So it's representing the answer in some abstract form here, involving integrals, and surprisingly perhaps, maybe not surprisingly, the cosecant function. Cosecant is 1 over sine, so I guess that's not surprising. Inverse function of that. I think the variable for this thing, by the way, is essentially that limit of integration with the pound sign. Hashtag. It's not a Twitter thing. By the way, I signed up for Twitter just like last week. I still don't get what Twitter's about. And my first tweets are like, I don't get Twitter. What's the point? I guess you can follow me if you want, if you're on Twitter. That's what my son said, by the way. The point is so that people follow you. I'm like, really? And you follow other people. Really? That's it? That's the point? Oh, okay, whatever. So it's representing the answer in some abstract form. That does have meaning, but it's confusing meaning, okay? It's not writing an ordinary kind of formula for it. It's not really giving it a name much either. We could give it a name. And we could approximate it with Euler's method, or probably something better than Euler's method. Actually, the most famous, better method is called Runge-Kutta. It's in chapter 7 if you're interested. Down here, solutions are increasing. Draw an upward pointed arrow. Down here, solutions are decreasing. Draw a downward pointed arrow. Or again, you can make this drawing on a separate vertical line. If you're going to label this vertical line with anything, you label it with the letter Y. If you got a point where nearby solutions are going away, meaning vertical arrow above, going up, downward arrow below, that's called a source, which makes sense. It's like it's a source of water, and water is flowing away from it. When you've got a point, an equilibrium point, where nearby solutions are heading toward it, over here, the solutions have that line as a horizontal asymptote as t goes to infinity. This is all as t increases to infinity here. Or actually, the solutions up here probably have vertical asymptotes, but don't worry about that. That's called a sink. The water is heading toward the point and going down the sink, so to speak. That's a little misleading. These horizontal asymptotes never touch the horizontal solution, so the water actually never reaches the sink. So it's a little bit misleading. Here they're going away, that's the source. You can have examples where solutions are increasing when they're below the point and increasing when they're above, or the other way around, decreasing in both cases. In either of those cases, that's called a node. You get nodes when your f of y function has a graph that just touches the y-axis tangentially, either like that or like this. That's when you get nodes in the phase line. This phase line idea seems a little strange. I guess one nice fact about it is you don't have to draw the entire slope field. It's quicker to draw. But more importantly for us, it's going to lead us to something called a phase plane for systems of two differential equations that are autonomous, and even phase space for systems of three differential equations that are autonomous in chapters 2 and 3. Okay, that's really the more important goal. But initially, it just seems like a quicker way to see the basic behavior of solutions. Up here, solutions for initial conditions greater than 2, solutions increase as t increases. And here, solutions decrease as t increases. And here they increase, and down here they decrease. Okay? So it's in the big scheme of things, it's not that difficult of an idea, but it takes some getting used to. And I guess that's the end of class today. See you next Monday.